Good morning. Welcome to the 36th lecture on economics, management and entrepreneurship. In our last lecture, we had covered multiple regression method as a forecasting technique. Regression methods are usually applicable to medium term forecasting. For short term forecasting, normally we use time series forecasting. In our last lecture, we had introduced the concept of time series, and we had said that a time series had got different components, and then we had said that there are principally three methods. One, the moving average method; two, the exponential smoothing method; and three, the Box-Jenkins method, which are also known as ARMA-ARIMA methods. Let us once again look at the components of time series and the first two methods, the moving average and exponential smoothing method. First, the components of time series, and we had said that there are principally four components: average, trend, seasonality and random noise. There is also a fifth component called autocorrelation, with the help of which one can identify whether there is trend or seasonality, and also in its own right autocorrelation is a component with the help of which time series can be modeled and can be forecast. And I had told you that suppose a time series does not contain a trend or a seasonality, but contains only an average and certain fluctuations around the average, then this is equivalent to saying that x t is equal to x t, the time series is equal to a constant A plus a noise term epsilon t. That is the first diagram, the noisy time series. The second diagram is noisy time series with a trend. It means that we have in the second time series, we have the time series x t expressed as a constant A plus a long term trend B, long term trend t and its coefficient B, and plus there is a random noise epsilon t. Thus, this is the equation of A plus B t, and on superimposed on that is random noise. Therefore, the actual values fluctuate around this. Then we have time series with seasonality and noise. So, whenever there is a seasonality, you will see that there is a regularity in the fluctuation. It has got a constant amplitude, almost a constant amplitude, and the periodicity is constant. Now, in this case, the average is there is a seasonality around the average and there is certain random noise, whereas here we have an average and a long term trend, and on that there is a regular seasonal pattern, and of course, there is certain amount of noise around it, and there can be different other variations of these components. Then we had also introduced the concept of correlation. Basically, correlation is a extent of linear relationship between two variables x and y. This is a case of correlation coefficient equaling 1. This is a negative minus 1, and these are close to 1 positive, but not 1, it's 0.85, and this is minus 0.88, negative but not exactly lying on a line. Autocorrelation is basically defined in terms of only one time series, but when it is correlated with its own past values. So, if we take autocorrelation between y t and y t minus 1, we then define y t minus 1 as a 1 period lag time series. So, 10 and 10, 15 and 15, 20 and 20, etc. A 2 period time series means 2 period lag time series means 10 here, 15 here, 20 here, 12 here, etc. And then we find out how y t is correlated with its own lag. That is autocorrelation, and correspondingly we can find out autocorrelation coefficient. Next, we had introduced the concept of time series smoothing. Basically, whenever there is a time series x t having certain old values, then we say its smoothed value is an weighted average of the past values, the weights adding up to 1 and each weight greater than 0. This we had used in certain examples. Suppose that we have 5 values of x t, and if the constant weight w t is given as 0.2 to each one, 0.2 is greater than 0, and when we add them 0.2 5 times because 1 becomes 1. Therefore, average of x t calculated at the time point 5 is equal to 0.2 into 5 plus 0.2 into 12, etc., equal to 11. Whereas, if we change the weights, still maintaining that sum of the weights is equal to 1, then the same quantity using the same values, the weights are different now, 0.5 into 5, etc., the value of x 5 is 10.5. And we say that if a time series contains an average and a noise superimposed on this, then the expected value of the time series at any time is nothing but the average itself, meaning the smoothed value of this. So, we calculate the smoothed value of x at time t and then project that as the forecast in the next time period. So, we say that the forecast at time t plus 1, when we are here, we say that the forecast of the time series at this point will be the average value calculated at this point. So, when we are here, for example, we shall calculate the average value of the time series at this point, and then we say that that is the forecast in the next time period. Now, the moving average period is basically that we take only a constant moving average period. Suppose we decide to take only the most recent n data points, that is the moving average period. We may have many more data points, but we will take only the most recent n data points. Then the average value will be calculated in this manner, the average of that, and when the next data point is available, we discard the old value and add the new value, and thereby we recalculate the value of x at time t plus 1. This was the example which we had considered in our last example before we ended the class. Suppose that we have the time series values for 8 data points, 8 time points. The values are 6, 8, 10, 3, 11, 10, 6 and 8. And suppose that we take the moving average period as 3 and calculate from here. It means that when we are at time period 3, we shall average these 3 values and take that as the forecast for the next time period. So, average value of this is 8, 6 plus 8 plus 10, 24 divided by 3 is 8. 8 is taken as the forecast for the next time period. And when we come to period 4, we shall discard this one, we shall instead include this in our consideration. So, we will consider the values 8, 10 and 3, that makes it 11 plus 10, 21 divided by 3 is 7. So, that is the moving average value calculated at time point 4, and this is taken as the forecast for the next time period. Similarly, we go to the next time period 5, we will consider again the 3 data points, recent data points 11, 3 and 10, that is 24 divided by 3 is 8. So, we take this as the forecast for the next time period. Like this we continue. Now, we can calculate the forecast error, which is defined as the value of the time series data at time t and its forecast made. For example, at period 4 we have made a forecast of 8, but the actual value is 3. Therefore, the forecast error is minus 5. At time point 5, the forecast error is 11 minus 7, 4. Time point 6, the error is 10 minus 8, 2, and so on and so forth. These are the forecast error. Now, suppose that the time series data is all the time increasing. There is an ideal case where there is no noise, it contains only an average and a trend component. You can see at time point 1 the value of x is 2, then next period it is 5, the increment is 3, next period it is 8, increment is still 3, 11, 14, 17, 20 and 23. So, if the time series data shows a consistently rising trend, whether single moving average will be a good method. We see once again that we take the moving average period as 3, then the moving average value at time point 3 is 2 plus 5 plus 8, 15 by 3 it is 5, and that is taken as the forecast for the next period 5. Next it is 5 plus 8 plus 11 divided by 3, and that is 8. And likewise, we see that the single moving average value consistently lags, meaning what was 5 is reflected in the next time period, what was 8 is reflected in the next time period. So, there is always a lag of one time period before it can actually reflect the current value. So, we can say that if n is equal to 3, that is the moving average period, n is equal to 3, the lag is 1, this 5 comes here after one time period, 8 comes here after one time period. So, in general this lag is equal to n minus 1 by 2, n in this case is 3, minus 1 is 2, 2 by 2 is 1. So, one time period lag, and we see that the error between x t and f t is a constant 6. Now, we can correct for this error to know or to be able to make a forecast very accurately. If we know or if we can make out what this error is, we can add to x t, x bar t to get this amount. This is shown in this figure, assuming that the value of x rises consistently in a linear fashion. Suppose that this is x t rising in this fashion. Once we make a single moving average, once we smooth it once, we know that there is a lag of some time, which is n minus 1 by 2. After n minus 1 by 2, this value is reflected as the smoothed value. We have already seen when n is equal to 3, the value was 3 minus 1 by 2. After one time period, this value was obtained as the average value. So, this value, this difference, the length of this line will be equal to n minus 1 by 2. Now, suppose that x bar t is smoothed once again, we call it double smoothing, and this is a single smoothing. Single smoothing of x t is x bar t. Double smoothing of x t is equivalent to smoothing the smoothed value of x t, meaning smoothing this. Now, if x t rises this way, x bar t also rises in this same fashion, but it is a lagged value, lagged time series, as we have seen in this diagram. This was 2, 5, 8 etc., and this was 5, 8, 11, 14, 16 etc., one time period lag, but it was also rising. Now, if this value is once again smoothed, then this will also be rising, but it will once again show a lag. And if the time period, moving average period is same for the first smoothing and the second smoothing, then this distance would also be the same, which is n minus 1 by 2, and this difference is x bar t minus x double bar t. This is the value of x bar t at time t, and this is the value of x double bar t at this time, and that is the difference. If we know the vertical distance x bar t minus x double bar t, and we know the horizontal distance, which is n minus 1 by 2, then we can find the trend, which is this divided by this. Therefore, we can find out A t. That means, suppose that we are interested to find out this value, this will be equal to x bar t plus this quantity, and this quantity is nothing but this quantity. So, A t is equal to x bar t plus x bar t minus x double bar t. This quantity is equal to this quantity. We have already calculated this. Therefore, this quantity will be equal to 2 x bar t minus x grand average, and the slope is equal to x bar t minus x double bar t divided by n minus 1 by t. Therefore, at this point, suppose that we are interested to make a forecast m time periods hence, then it will be this plus m times b t. If it is to the next time period, then m is equal to 1, then the forecast for the next time period t plus 1 is A t calculated in this manner plus b t, which is this. Now, let us introduce another important, in fact, more important than moving average method is the exponential smoothing method, because of its simplicity. Once again, consider n data points of a time series, but we are writing backward, defining backward, meaning that the most recent value is x t, one period old value is x t minus 1, 2 period old value is x t minus 2, n period old value is x t minus n plus 1. We write it backward, and then in order to smooth, we have to attach weights. Let the weights be alpha t minus 1, alpha t minus 2 and alpha t minus n plus 1, and we define alpha t as equal to alpha, alpha t minus 1 as equal to alpha into 1 minus alpha, alpha t minus 2 defined as alpha into 1 minus alpha square, like that, and keeping in so that alpha is greater than 0, but less than 1. And as we know, in order to find out the smoothed value, the weights must be such that they have to be positive, but at the same time must add up to 1. So, alpha I sum will be alpha plus alpha into 1 minus alpha plus alpha into 1 minus alpha square, and so on and so forth. If n tends to infinity, then this quantity is nothing but alpha divided by 1 minus alpha. it is a geometric progression series with a progression ratio equals 1 minus alpha, which is greater than 0. Therefore, in the numerator the progression, when we add it up, it will be alpha divided by 1 minus alpha, and that will become 1. So, if we define the weights in this fashion, then the sum of the weights is equal to 1 and each alpha is greater than 0, but less than 1. You will see here that if alpha is less than 1, then 1 minus alpha is also less than 1, and alpha into 1 minus alpha will be less than alpha. In the similar fashion, alpha into 1 minus alpha square will be less than alpha into 1 minus alpha, like that. It means that if we associate the weights in this fashion, then weight associated with the most recent data point is the highest. The weight associated with the next data point, one period old data point, is less than that associated with the most recent value, and it is a decreasing sequence. So, the weights have their values in a decreasing sequence. The highest value of the weight is given to the most recent data and the lowest value given to the oldest data. This is shown in this fashion. It is a decreasing sequence of data. Of course, this is shown in a continuous manner. If t is continuous, then alpha will decrease continuously in an exponential fashion, and that is why the name of the technique is exponential smoothing technique, because the weights associated decrease in an exponential manner, in a negative exponential manner, as if t is assumed continuous. Now, the exponentially weighted average is written as x bar t equal to alpha x t plus alpha into 1 minus alpha x t minus 1 plus alpha into 1 minus alpha square x t minus 2, and this is nothing but alpha x t plus, if you take 1 minus alpha outside, you get alpha into x t minus 1 plus 1 minus alpha into x t minus 2. So, that is nothing but x bar t minus 1. So, the exponential weighted average x bar t, which is really a big expression, can be shortened in this fashion, which is that a weight is given to the most recent value alpha, and 1 minus alpha is another weight given to the old average of x that was calculated one time period ago. So, x bar t is alpha x t plus 1 minus alpha x bar t minus 1. Now, whenever there is only noise and average value, we take the forecast for the next period as f t plus 1 as equal to x t itself, because expected value is a, and if it has no trend, no seasonality, then f t plus 1 will be nothing but equal to the average value a x bar t. So, our exponential smoothing formula is really this, and when used as a forecasting method, then instead of x bar t we could as well write f t plus 1, f t plus 1 as equal to alpha x t plus 1 minus alpha f t. Instead of x bar t minus 1, we can write f t. We can take an example to illustrate the use of exponential smoothing method. Let the time series have a value such as this, and how many values we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 values. So, t equal to 1 through 9, and the values are like this. We can see that there is a noise in it. Looking at it, we can say that there is a noise in it, and there are fluctuations and we are not very sure whether there is a seasonality or not. Now, if you see, we need, in order to use this equation, we need to have the past value x bar t minus 1, and in this example we have only the actual time series values. We do not have any past smoothed value. So, we must have to start with an initial value of x bar t. So, we can in fact arbitrarily take 2 or 3 values, 3 initial values, old values of the time series, and use a moving average of the first 3 such data points to find out the initial value to use our exponential smoothing method. In this example, we have taken the moving average period as equal to 3. That means, we have taken the first 3 data points 16, 11 and 13 and find out an average value of that, moving average value. So, 16 and 11 and 13 added divided by 3 gives us 13.3. 13.3 is taken as x bar 3 and is used when we go to the next data point, next time point 4 and data value 12. Then we take x bar 4 are as equal to, we can use our exponential smoothing formula now. We can say it is alpha into x 4, namely 12 plus 1 minus alpha x bar 3 that was calculated from our moving average method. Once we have x bar 4, we can move ahead and use that x bar 4 here to calculate x bar 5, and we can recursively use that equation to go further ahead. This is the way we proceed when we use exponential smoothing in a recursive fashion. Now, this is what we have tabulated in this table. First of all, recall that we had calculated x bar 3 as equal to 13.3 and the values of the time series data were this. Now, x bar 3 was 13.3 and suppose that we take a value of alpha as equal to 0.1, then the next value would be alpha multiplied by 12, alpha is 0.1, 0.1 multiplied by 12 is 1.2 plus 1 minus alpha, which is 0.9 multiplied by 13.3. Let me do it here. We had the data points 16, 11, now the average we have calculated here as 13.3, that is x bar 3. To calculate x bar 4, we take alpha into x 4 plus 1 minus alpha x bar 3, and that is equal to, suppose we take alpha equals 0.1, then this is 0.1 into 12, because this is x 4, 12 plus 1 minus alpha is 0.9 into 13.3, which is x bar 3. This is equal to 1.2 plus whatever it is coming, and that is equal to 12.9. So, this is how the value is calculated, x power 4. And now, once you have x power 4 value, go to the next one, you have to take 0.1 into 12.9 plus 0.9 into the x 5 value, which is available as 20, and likewise you calculate x bar t for all the values. Now, suppose instead of taking alpha equal to 0.1, I take alpha equal to 0.9, because alpha can take a value from 0 to 1. Then the corresponding this value remains same, because that is what was calculated on the basis of the moving average value, but these values would continue to change. But we use the same formula. Now, we plot it here, this is time and this is the data values. The farm line in blue is the actual time series data, which was 16, then 11, then 13, then 12, 20, etc. So, this is the actual time series data. Smoothed values on the basis of moving average was calculated here at time point 3, and if we use 0.1, the red dotted line is this, the value behaves in this fashion, x bar t goes down a little bit here and then slowly rises, does not consider so much of fluctuations. It does recognize that there is a rise in the average value. The average here was much less, but the average here was much higher. It is trying to, it is increasing, but not at a very fast rate. And when we had taken alpha equals 0.9 instead of 0.1, the red, brown red maybe, that line, dotted line is closely following the actual value. Okay. So, it means a higher value of alpha gives the higher weightage, a higher weightage to the most recent data and low weightage to the past data, and therefore, it has a tendency to track the change quickly. Its response is fast, whereas when we take alpha equals 0.1, then it is unable to track the underlying change and it smoothens the fluctuations quite a lot. This is shown here. Suppose that there is a step rise in the value of the x, that is the time series data. Suppose, so if there is no noise, no train, no seasonality, etc., then the average value remains same, but when there was a step change with a small value of alpha, it increases slowly, but with a high value of alpha, its response is very fast. That is the advantage of taking a higher value of alpha, because it gives higher weightage to the most recent data, and that is close to 1. So, a low value of alpha gives less weight to the most recent data, it smoothens out noise, but it cannot track the underlying changes very fast. Whereas, a high value of alpha gives more weight to the most recent data and tracks the underlying change quite fast. Now that we know that the value of alpha can be high or low, and a higher value of alpha is able to track the underlying change, but the lower value of alpha can smoothen out random fluctuations. If the data does not contain any underlying any trend, but we use a higher value of alpha, then it will have a tendency to even track the random noise. That means, the forecast would be as noisy as the original data, and that is not what we want. We would like to track only when there is an underlying change in the value of the average. We do not want to track the noise. So, whenever we do not foresee any change, permanent change in the average, the change is noisy, the change is random fluctuation, then we use a small value of alpha. But if we have strong reasons to believe that the average itself is undergoing a change, then we take a higher value of alpha. This has led to using a method where alpha is changed adaptively. So, that is called forecasting with adaptive smoothing constant. This alpha is called smoothing constant, and we change the value of the smoothing constant. We change it depending on the error, forecast error. Now, this is an example. We visualize first of all in this diagram first. Let us say that in the beginning there was not much of a change in x t. So, we can take a small value of alpha, but here x t is undergoing a change, almost a permanent change is occurring. So, we should be able to understand that there is an underlying change, and therefore, change our alpha from a low value to a higher value such as 0.8. So, that it quickly tracks the change, and once this is more or less stabilized, there is not much of a change, it is stabilizing, then we reduce the value of alpha, so that the noises are not tracked so much. So, this can be done by using a method which works in this fashion. Here we first of all find out the error. Error we have already known, x t minus f t, that is the error. So, that is E t, E t is x t minus f t. So, error is first of all smoothed, giving a smoothing constant beta, beta E t plus 1 minus beta E t minus 1, exactly the similar formula to find out smoothed error. Then the smoothed absolute error we find out, that is E t absolute value, and find out its smoothed value, we call it smoothed absolute error. The ratio of the smoothed error to the absolute error is taken as the smoothing constant for the next time period, and this is used in our calculation to make the forecast. And this is how one can change alpha. Here for example, if we continues to use alpha equal to 0.1, the forecasting error will be high. When the forecasting error is high, alpha will be changed following this formula, and that will give a higher value of alpha. And at this point, when forecast error will come down, then alpha t minus 1, this value will automatically be reduced to a value close to 0.1 or so. This is the forecasting method with smoothing constant that adapts itself with the forecast error. Now, if the time series contains average, trend and noise A plus B t plus epsilon t, then what is done? First of all, we calculate the current trend. Current trend is x t minus x t bar minus 1, of course, divided by one time period. So, it is x bar t minus x bar t minus 1. This is once again smoothed, because there may be some fluctuations around the trend. Trend may not be a permanent trend. So, we smooth the current trend, and use that current trend to project the future. So, one time period projection is x bar t plus just t bar t, that is the forecast for the next period, and x bar t is calculated following our exponential smoothing method. If it is a mth period forecast, then it is m t bar t. So, this is when we have a time series that contains an average A, trend B t and the noise. Now, when we have seasonal data, then what we do is to first of all deseasonalize. Suppose that we have data that goes up like this, then what we do is find out an average value and find out to what extent the ratio of these values from the average. So, that they are the IT values. I is the seasonality index. We calculate first of all an index I. So, if we divide this by that I, we get this, that is the idea. We divide this by I, we get the average value. We divide this by I, we get this. So, first of all the values are deseasonalized. So, we have to find out initial value of I, which is smoothed once again later, as you can see here, using similar equation. X t minus x bar t is basically I t and it is the current seasonality index. This is the L period back calculated. L is the seasonal period of seasonality. So, this seasonality smoothing is done here, overall smoothing is done here, and we work with the deseasonalized data x bar x t prime. X t prime is defined in this fashion. As usual, as before, current trend is calculated and smoothed, and I is smoothed. The forecast finally is the smoothed value calculated in this fashion plus the m period ahead trend added to it, multiplication the seasonality index calculated for the mth period ahead. This is how exponential smoothing is used for seasonal data. Before we close our lecture, we would like to just give an introduction to a very useful, but highly sophisticated method of forecasting, which is known as Box-Jenkins method or ARMA-ARIMA method. We will just give an introduction to Box-Jenkins method introduced by Box and Jenkins. Also known as ARMA-ARIMA method. We just give an example. Suppose we already know that f t plus 1 is equal to x bar t, that is smoothed value calculated at t time period t is taken as the forecast for the next time period, and that is known as alpha x t plus 1 minus alpha x bar t minus 1. Now, we can write this, we can write f t therefore, as nothing but x bar t minus 1, and we can write x bar t minus 1 using it recursively as x t minus 1 plus 1 minus alpha x bar t minus 2. And this can be written as alpha x t minus 1 plus 1 minus alpha x bar t minus 2 can be written once again recursively as x t minus 2 plus 1 minus alpha x bar t minus 3. So, like this if we proceed, we shall get x t minus 1 here plus alpha into 1 minus alpha x t minus 2 plus alpha into 1 minus alpha square x t minus 3, and we will proceed like this. We can therefore write, you can see that forecast for the time period t is a function of the time series data x at 1 period lag, 2 period lag, 3 period lag. Therefore, there is a regression, this is a regression like equation, and if we replace f t as x t, we can say this is a 1 x t minus 1 plus a 2 x t minus 2 plus a 3 x t minus 3. So, this is called an autoregression or an autoregressive model. Keep this aside and now have the moving average form of the same thing. Now, if we write f t plus 1 as equal to alpha x t minus 1 plus 1 minus alpha x bar t minus 1, we can write this as alpha x t minus 1 plus 1 minus alpha f t. Forecast for the time period t is the average calculated at t minus 1. Therefore, we can replace x bar t minus 1 by f t. This we can write as f instead of f t plus 1, we can now let us write f t. F t will be equal to alpha x t minus 2 plus 1 minus alpha f t minus 1. This we can write as 1 into f t minus 1. Therefore, we write f t minus 1 plus alpha times x t minus 2 I am sorry, there is a there is a mistake here. Now, let us redo it, there is a mistake here, I am sorry. F t plus 1 is equal to, we know x bar t. So, f t is equal to x bar t minus 1. Now, this is equal to alpha x t minus 1 plus 1 minus alpha f t minus 1. This is equal to f t minus 1 plus alpha x t minus 1 minus f t minus 1. This is nothing but the forecast error. In fact, one interpretation of the exponential smoothing forecast is that forecast is the old forecast plus the forecast error given some weightage alpha. Now, we can expand f t minus 1 like before. We can write f t minus 2 plus alpha e t minus 2. If we call this difference as error E, and this we can write E t minus 1 error. So, if we proceed this way, then we will land up with writing this first alpha E t minus 1, next this alpha E t minus 2, and like this. So, in general we can replace f t by x t, and we will say that x t is equal to b 1 e t minus 1 plus b 2 e t minus 2 and so on. So, this is normally called a moving average form. Remember that this moving average is not the same as the moving average that we had used earlier, but unfortunately this term moving average is used in this sense. Now, if we use this form, which is the autoregressive form, where x t is regressed or related with its own past value, and this is the moving average form where x t is related to the forecast error. If we combine the two, we get what is known as ARMA method. We will say A R 1 as equal to as x t equals some constant mu plus phi 1 x t minus 1 plus E t. Similarly, M A 1 we shall say x t as equal to mu plus E t minus theta 1 E t minus 1, and we will say ARMA M 1 is x t equal to phi 1 x t minus 1 plus mu plus E t minus theta 1 E t minus 1. Basically, what we are trying to say here is that exponential smoothing method is equivalent to some sort of an autoregressive model and some sort of a moving average model of the form that I had just now developed. AR 1 is only one period lag value is taken, that is why it is autoregressive of order 1. This is a weight phi, this is a constant mu, and this is the error term E. In the moving average form of order 1, only one period lagged value of the forecast error is taken, which is given a weight theta, and this is the current forecast error, that gives a value x t. And if we use both autoregressive of order 1 and moving average of order 1, then x t will be equal to phi 1 x t minus 1 plus mu plus E t minus theta 1 E t minus 1. Now, these are what is called the very elementary forms of autoregressive and moving average models used in the Box-Jenkins methodology. And for short term forecasting that considers autocorrelation, these ARMA methods are quite important. However, time does not we do not have sufficient time to discuss these methods. We have spent nearly 4 hours on long term forecasting, which is mostly qualitative, and medium term forecasting, which is usually regression based, and short term forecasting that makes use of time series data, in which we have introduced moving average methods and exponential smoothing methods. We said that exponential smoothing methods are more convenient to use, and it can be applied in various situations very easily. But the most advanced method of time series forecasting, which is based on ARMA, that is autoregression or moving average concepts, we just introduced. We will not be able to discuss them in course of these lectures. Thank you very much.